So now we're going to officially begin Module 5, which is covering rotating machines in general with a specific focus on synchronous machines. So what I want to do is introduce the three main types of rotating machines that we will be covering in this class. There are a much wider range of rotating machine types that are out there, but these are the most commonly found, and I would imagine that many of you will encounter these machines in one way or another in your careers. And if you look around your house, you look around your car, look around any factory, any building, you're going to see these machines, especially the induction motor, which is the most common, and I would say probably the greatest invention ever invented by Nikola Tesla, of course. But I want to start with the most general of the machines, and that is the synchronous machine, which is what we will focus on in this. Now, as we had spoken about this in the prior module, lectures on Chapter 3, in general, rotating machines will have two effective windings, and we will explain what I mean by that as we proceed. One of those windings we will call a field winding, and it provides a magnetic field, or we could basically call it an electromagnet if we were to have what is called a permanent magnet machine. And we didn't have time to cover permanent magnets in detail this semester, unfortunately. But if we have what we would call a permanent magnet machine, it would use a permanent magnet for a field. And the big benefit of that is higher efficiency, because there are no losses associated with the field, and higher what we would call power density. Power density is essentially the ratio of output power, S, and I would say this is mechanical output power, to volume. And that equates to lower cost overall. And it also is dependent on the type of magnet. The most common being, in our day today, rare earth magnets, such as neodymium iron boron. So the second type of winding, or effective winding, in most of these machines that we're going to talk about, or the majority of them, is called an armature winding. And really, the armature winding is associated with the torque that is produced if it's a motor, or the torque required to achieve a certain power level if it is a generator. Now let me just in general define what I mean by machine. I've got a little bit ahead of myself on this. A machine means a motor or a generator. So it's a general term for that. Now, the second type of machine that we are going to talk about in this class is a DC machine. So far we have a synchronous machine and we have a DC machine. Now these two machines are very similar, as you'll see very soon here. But there are some distinct differences between them that I'm going to point out and that you should pay attention to. The third type of machine that we're going to talk about is, in general, called an asynchronous machine. Now, an asynchronous machine is most commonly referred to as an induction machine. In this class, we will be focusing only on the induction motor. The induction generator is a very different beast, and the induction generator is something that is quite complex and something that we won't be discussing. So these are the three machine types we'll cover in this class. Now I know that I'm giving you a lot of hints of things to come, but there's a lot to unpack here, and so I'm going to start with the synchronous machine because it's really a very general machine, and the synchronous machine is very important in its use. It is really what is behind all of the power generation that we have in our world. So when you think of synchronous machines, the synchronous generator is behind every power plant that depends upon rotating motion to produce power. So this is one reason why a synchronous machine is really important. Another reason why a synchronous machine is important is because of the synchronous machine functionality is really it's really the foundation of all controllable power conversion, electrical power conversion that connects to a three-phase grid. Essentially, that's what our electrical grid is. And so a lot of the concepts associated with synchronous machines need to be understood in order to understand, for example, how renewable generation occurs from wind power, for example, and how to control power flow using power electronics when you're interfacing with a grid. So this isn't something that we cover in this class, but it's really the reason why synchronous machines is covered as an undergraduate foundational topic, because the synchronous machine knowledge, if you go on to work in these very important areas, is really underlying a lot of the theory and a lot of the really interesting things that are going on. So this is enough of the general stuff, and so let's now just get into the meat of everything. I want to start by returning to this picture of the DC. This is how we introduced Lorentz Force Law, if you'll recall. And we were pointing out that in order to have produce torque on a rotating shaft, or a shaft that is allowed to rotate, we needed two things. We needed to have a magnetic field, and the magnetic field is represented by these green lines here. So this green area right here represents a field the electromagnet that we talked about, the field electromagnet. So this green area here represents the electromagnet that is producing the magnetic field. This is the current that's going in to that winding, and then you can see the current coming out right here. So you would create a iron core structure, which is what is shown right here, and you might call that a back iron or the stator, or it's also called a yoke that holds the field in place. The second thing that we showed that we needed was we needed to have the current for torque production going through this blue winding here. So I've got the current, and imagine that this current is flowing into these wires here that are on the rotor. So there has to be a means for the electrical wires to connect to something that's rotating and produce this current in the winding. And the winding would be wrapping axially down the z-axis here of the rotor, and then coming back on the other axis. So this is the main current that's in the field path, and it's responsible for the Lorentz Force Law expression, which was this. And then from that, the torque, which is the translation of the force into the rotational domain, starting from the center of the axis out to wherever this armature winding is. So we would be doing another cross product there with force to get a torque. Now I want to talk about how does this current get onto the rotating shaft. The way that it does this is through a electrical and mechanical assembly made up of brushes and commutator segments. I'm showing here in this cartoonish picture the brush. It's this little rectangle right here, and the wire connects to the brush. And then it's a carbon type of material. And there has to be two brushes, one for the supply and another brush for the return, in order to provide the current into the armature. Now the brushes ride on top of a conducting copper segment, 2 segments as minimum, but usually there's multiple segments. And think of it as a copper ring that is right here, wrapped around the shaft. And then it's cut. There's a cut made right where the brush is located here. And the brush is stationary, but this thing is rotating. And there are these 2 gaps. What happens is the current flows through the brush, and I'm showing it right on the gap, but it could have been moved just a little bit, let's say counterclockwise, and it's touching this copper piece right here. And the current is flowing through that copper segment of the commutator, and it's connecting up to this winding right here. And it will continue to flow through that point as the rotor is moving around in this direction until it hits the next little gap and the segment that connects it to the other side here. And at that point, it's going to flip the polarity of the current. The effect of this is that it maintains a fixed direction of current with respect to the field flux, regardless of the position of the rotor. We'll show this in much more detail when we get into Module 6 and discuss the DC machine. The bottom line is that you get the current onto the rotating part through brush and commutators. Now, the interesting thing that you can do with the commutator segments and the armature winding is that you can arrange them such that and this is for this very simple two-segment commutating ring I'm showing right here and here. The wire coming from that, connecting it to the top supply part of the winding, and then coming back and connecting back to the bottom segment here. And by orienting it such that this winding, orienting this so that this winding is essentially in quadrature or 90 degrees out of phase with the field winding, what will happen is you will end up with this torque angle being equal to 90 degrees. As a result, the torque produced by this DC machine, if it is a motor, would be equal to the negative of the turns on the armature times the flux times the armature current sine of negative 90 degrees, which is a positive number then. And if it's a generator, the torque would be same expression, sine of positive 90 degrees, which is negative of the turns times the flux times the current. So we can see that we can get the full amount of torque for a given amount of current because of this angle here. Or if we want to get a certain amount of current out of this, then because of this angle, we can only need a minimum amount of torque going in. So let's talk about the synchronous machine. The synchronous machine is different. It's, in a sense, I'd like to say that the DC machine is an inside-out synchronous machine, starting with the synchronous machine as a more general case. The synchronous machine, though, has the field winding here is on the rotor. So notice that the green color for field has now been moved from the stationary to the rotating part. The armature winding, which is now, I'm going to call this an equivalent armature winding, and we'll make that clear what that means as we proceed. That happens to be on the stator now. Now, how does the current get into the field of the rotor? The current gets into the field of the rotor, and again, if I hadn't made this clear before, the field current, in the case of the DC machine, of course, the currents in the field and the armature are both DC currents. But in the case of the synchronous machine, in the case of the DC machine, the field current is DC. But in the armature, the current is AC. And how this DC current gets onto the rotor is, again, it does use brushes shown here. And they are riding along these copper rings that are on the rotor. And there are two of them, one ring for supply and one ring for the return of the field current. So the current goes in through the brush and it goes onto one of these slip rings here, which connects to the coil that's on the rotor. The coil on the rotor comes out and through the slip ring into this brush here, and it returns from some DC supply or DC source of current. So that's really what the structure of the synchronous machine is. So let's look at the magnetic circuit for the synchronous machine. For the moment, I'm just going to look at what we're going to refer to as a simple synchronous machine, where we have the field winding shown here wrapped around this salient or dog bone shaped rotor. So the current is coming in here through slip rings, would be coming out, it'd be wrapping around, and it would be coming out here, the winding with the field current in it. And there are going to be a number of turns, which we'll refer to as field turns, NF. And the current that's going in here we'll refer to as the field current, IF. And there are quite a few field turns, probably hundreds to thousands of turns on any synchronous machine. If we were going to consider the fact that we have, because of this field, we have a flux that is created, and it's following this magnetic circuit going and splitting up in two on both sides of the back iron here, flowing in this direction, taking right-hand rule. We could see that effectively we've got a north and we have a south pole that's created. The flux density in the air gap will be different at each position. So this diagram here to the right from the textbook shows that the flux density at let's say that we're at a given position of the rotor, and the rotor is being held in place. At the position where we're crossing the gap at a minimum distance, we will have some peak flux density. And this peak flux density right here would be associated with the north pole of the machine. And then coming around the other side, so essentially traveling, I'm going to travel in this distance here. Let's say we're traveling in this direction here as we're measuring the field flux density in the gap. We'll come around to this point right here where we have the south, and that would be a negative peak of the flux density. What we will assume right now is that this rotor shape is such that it shapes the field distribution inside of the air gap to make it look relatively sinusoidal, like this picture right here shows. So the flux density distributes around 360 degrees of the rotor. Now, what if we were to change the rotor structure to make it look like this? And what we've done in this case is we have increased the number of poles. So what we're looking at right now is what's called a 4-pole synchronous generator. And the structure, instead of being this dog bone structure here for this simple synchronous machine, another word for this type of machine is a salient pole synchronous machine. The textbook talks a lot about this type of machine later, and the details of it, but we're not going to go into a lot of detail with it right now. But if we have this machine here, imagine that we have a field winding that's being wrapped around each one of these little parts of this T structure. So we've got, current coming in here, coming out here, and then it gets wrapped over to here, comes here, wraps over to the other side here, comes back around, wraps over to here, connects over to here, and wraps around this piece here and comes out. So you've got your field current going in here. So this is a 4-pole machine. The result is that you've got a north and a south, a north and a south. So the flux density distribution, there's one of your norths right there. And again, it's shaped to be as close to sinusoidal as possible. There's a south, a north, and a south. And that is your 4-pole machine. What I want to do now is to analyze the magnetomotive force, or the MMF, that is going to be produced by the field winding. And that's the MMF that's behind the flux density that we were just discussing. Now, the way that we do this with a rotating machine is we look at the rotor, which is shown right here, and we kind of flatten it out, make it look like it's just this flat, rolled out thing. And we look at the current going into the coil, and we're going to look at this 4-pole machine. And the way that these machines are built is that these coils that have the current flowing in them, like right here, 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 and here, have they're placed in slots in this ferromagnetic material. And in order to understand how the MMF is developed by this field winding, we walk along this flattened out rotor structure, starting at this position right here. So this is at a position along the rotor, and for that reason I'm going to call this theta R, rotor position of 0. And we are going to proceed along here till we get back around to 2 pi. And so this point right here and this point right here are the same point. We just come back around onto it. And we're going to count the conductors and the current that's flowing through them as we proceed. And we're going to treat the current right now as if there's a little dot. You can see the dot coming out right here, that the current coming out, we'll say that's a plus plus current, a positive current or increase of current if we encounter that point of 1 amp. It could be any current level, but we're just going to consider 1 amp so that it doesn't change the number that we're going to come up with. There is a certain number of turns per pole inside each slot. And the MMF does not change at all until we get to the other side of this winding. And in that case, where the current was coming out, it's going back in. And so we say, okay, at this point, because it's going in the opposite direction, the MMF, total MMF has gone down to 0 again. Then we're going to proceed along here, and we're going to hit another coil in this slot, and since it's coming out, it's going to make it go back up to a positive value. It's going to stay there till we come back around to this one here where it's going in, and it's going to go back down to 0. And what we've done is we have created a function of magnetomotive force, or MMF, that is position dependent with respect to this position along the rotor. And at this point, what we want to do is let's just take an average of what that MMF is that we've created. Since these distributed coil positions are equally distant and the resultant is always positive, we're going to end up having an average MMF. And that average MMF is what I'm showing by this line right here. That's 1/2 of this value. And so now it becomes NF over the number of poles. The next step is to subtract off that average from that MMF function. And what we end up with is what we call a turns function. If you were to divide out the current, it was already set to 1 for our example. And so the shape of this and the amplitudes haven't changed, but they're centered around 0. And so we can have a plus NF, or we could have a minus NF. And this is referred to as a turns function. Now, when the synchronous machine, what we're really interested in is we're interested in the effective sinusoidal distribution of the MMF. So this is going to be what I'm going to call the sinusoidally distributed part of the turns function. What I mean by that is that you have a square wave, you have a non-sinusoidal shape, but any periodic shape through the use of Fourier series can be decomposed into a number of sinusoidal parts that are at different frequencies. And when I say frequency, I mean a period. And we have two periods that are occurring in this frame here from 0 to 2 pi because we have what's called a 4-pole machine. And because of that, we can come up with a turns function that is varying twice per rotation. Now I want to go back to this idea before I show you the turns function, and let's talk about the effect of the poles. And let's specifically look at this function here of the flux density. If I go back to the 2-pole machine, I could say that I have a flux density that is a function of some general position, which right now we're calling theta A, along inside of the gap. And that's what we were talking about when we were talking about the flux density. So the flux density becomes a position-dependent term. It's a function of theta. In this case, we're saying theta A because that's the position inside of this gap right here. It has some peak flux density value. This looks like a sine wave, so we'll say this is a sine of theta A. If we look at the four-pole machine, we could come up with another function. So this would be B theta. We've got some B peak. It's a sine function. Because we have two peaks, it's going to be 2 times theta A. What I want to do is introduce the idea of an electrical angle. The electrical angle eventually is going to be what we have been calling all along theta E. So that should look very familiar to you. So I'm going to relate this to this physical mechanical position through a function. And so in this case, I'm going to eventually drop this sub A to make this completely general. But we have a theta A that's electrical equal to the number of poles divided by 2 times the physical position. So this term right here is referred to as pole pairs. Since we have 4 poles, then the pole pairs is 2. That's this thing right here. So we could rewrite this expression in terms of electrical angle, and it would be the peak flux density times the sine of the theta AE electrical angle, where the theta AE is equal to this function. So this is the first extremely important formula that we need to remember regarding synchronous machines. The theta electrical is equal to the number of poles divided by 2 times the mechanical position. So I could say theta mechanical even if I wanted, and say, okay, that's what we have here, a relation between the mechanical angle and an electrical angle. Now let's go back to this turns function, and we're going to write a turns function in the same way, and it's going to be a function of a mechanical angle of the rotor right here. I'm really only interested in the sinusoidal fundamental, which is the first harmonic of this square wave thing here. So that's n sub 1. And if you were going to take a Fourier series of that, and you know that you've got NF divided by poles as the peak of this square wave, then the sinusoidal function would be this. N1 is a function of theta r equal to 4 over pi times NF divided by the number of poles. So this is essentially your N1 peak times the sine of the pole pairs, poles over 2, times theta r. So what I want to do right now is drill down a little bit more on this turns function and analyze it a little bit. We have talked about the fact that this machine is a concentrated winding machine, which means that all of the turns are concentrated inside of a single slot for the supply and a single slot for the return for each pole. The second thing is this type of winding that we're looking at would be called a full pitch winding, which means that the distance between the supply and return of each coil is one pole pitch. So the pole pitch really would be defined as 180 degrees divided by the number of pole pairs. So if you had poles equal to 2, the pole pitch is 180 degrees. If poles is 4, the pole pitch is equal to 90 degrees. And you can see that we would have 4 of the 4 pole pitches for the 4-pole winding. So a full pitch winding would have a pitch factor Kp equal to 4 over pi, assuming the concentrated winding as a starting point, and then we would modify the total, what we call winding factor, by multiplying this pitch factor, which is the 4 over pi, times a distribution factor associated with the particular winding and its harmonics. So we could have in general a winding factor for each harmonic, which would be kW sub h. Therefore, for the field winding, so I'll say kW, and this is just for the field, sub h would be equal to 4 over pi, and it's a concentrated winding, and therefore the distribution factor ends up being 1 over h. So if we wanted to have a function for the turns that reflects this exact shape, that function for the field winding as a function of theta r would be equal to the sum from h equal 1 to infinite number of harmonics, 4 over pi times the harmonic distribution factor times the total turns per pole times cosine of h pole pairs theta r. So here's a final result for any winding, and I'm going to show you a different way that the winding can be produced in a moment. And we've also described the fundamental component of that winding by this factor here. This is for the full pitched concentrated winding. Now we're going to turn our attention to a different type of a rotor structure. This is what would be referred to as a round rotor or non-salient rotor structure. This rotor has a uniform air gap, so the air gap as a function of theta r is a constant, so it's going to always be equal to some air gap distance G, some air gap length, as opposed to salient structures that we have introduced, such as this two-pole dog bone shaped field rotor, or four-pole dog bone shaped T kind of shaped four-pole rotor. And in this case, for these two types of rotors, the air gap as a function of theta r is variant. If you recall, we're going back to when we were talking about energy conversion, and we introduced a permeance function that would be varying as a function of theta r. That would be coming from this air gap function here. So the permeance function would be G theta r if it's only in the air gap, so we're assuming that the permeance or reluctance of the motor, of the rotor and the stator are infinite. The iron parts are infinite. And this would be the area that the flux crosses the air gap. So that is this area right here, or that area right there. That would be the permeance function we talked about in the last lecture. So recall, the permeance was 1 over the reluctance. So with these rotating machines. Now if we went to this round rotor machine, our permeance function would just be P naught equal to G over mu naught, whatever the area of that gap is. So the position dependency, which is necessary for energy conversion, in this case is going to come only from the turns function. And that's why I'm putting some emphasis on this. Now what we have with this round rotor structure, we put the turns into slots, but since we've got all this real estate that we can put these turns into, we can distribute them into slots. So we could distribute, for this is for a two-pole machine, we could distribute all of the supply sides or ends of the coils over half of the rotor, and then distribute the returns over the other half of the rotor. If we had a four-pole machine, we would just have this, would basically have a supply, these would be returns, they'd be dots, supply, okay, so that would be, these would be X's, and then we'd be back to dots again. So that's a four-pole way of looking at it. Now this is what the MMF, or this is what the turns function would look like for that field winding. And we would have this mathematical representation of it. It looks a lot like the turns function that we derived right here, only we've got another little factor. This was the KF, or KF1. It's equal to 1 here, but here it's not equal to 1, so we have to add that factor in, and that takes into account the distribution of the turns into slots. And so as we become more distributed, as the winding is more distributed, and you could think of it, or the slots it is in increase, the KF gets smaller. So KF is less than or equal to 1. And it's equal to 1 if you just had one slot per pole per coil end. And now that we have this position-dependent turns function, it follows that if we were to put a constant field current into the winding associated with that turns function, we could get an MMF here. So this is the field MMF. And now we have a function for the field MMF as a function of the field turns, the winding factors, and the number of poles. And it is a position-dependent terms. Okay, so where is this all leading? So let's not forget, we're really still talking about a magnetic circuit, and therefore we can think about coming up with a flux ultimately that is equal to the MMF divided by the reluctance, or equal to the MMF times the permeance. What we're trying to get into in general is we're trying to come up with a flux linkage between two windings that is a function of the rotor position, theta dependent. So that would be some other turns for another winding times this flux that we've come up with, and this flux has a rotor position dependency. If we could do that, we would be able to come up with a voltage associated with the movement of the rotor. By Faraday's law, that would be the derivative of theta r with respect to the movement of position. Ultimately, we can start to talk about energy conversion and torque and tie this back to what we learned in Module 4. Now, what we can have to get this position dependency, we would either have a MMF that is essentially uniform times a permeance that has a theta r dependency, and that's essentially the kinds of examples that we're talking about in Module 4 associated with Chapter 3. Or we could have an MMF that has a position dependency times a constant permeance, and that is what we're talking about right now, considering this round non-salient rotor structure. Well, let's go back again to the flux density we were talking about up here. Recall when we were describing the flux density, that's the flux density associated with the flux under one pole. And ultimately, we want to come up with what is that number? What is that flux number per pole? It's going to be associated with this sinusoidally distributed flux density. That flux density was driven by the field MMF. So if we go back down to look at this here, we're going back to a flux density. If we move the rotor, that flux density position will move. And the rotor will move at a constant rate, or a rotor speed. So we're going to call the rotor speed omega r, which is the derivative of the position with time. This is the angular velocity of any angle that's moving. We've really talked about this concept before. If we wanted to integrate both sides, we could say I have a theta r position that's equal to omega r times the time. So I could actually plug that in there. And now I'm back to this expression from Faraday's law that I'm very comfortable with, which is the derivative of the flux linkage with respect to time. The one more point that I'd like to make is we've talked about the electrical part of our energy conversion system. This is going to correspond to what we've talked about all along with AC machines, AC systems, where we have an electrical frequency that's equal to 2 pi, an angular electrical frequency that is 2 pi times the electrical frequency. This electrical angular speed corresponds to the rotor speed in a synchronous machine. So it corresponds in this way. Omega E is equal to the pole pairs, number of poles divided by 2, times the rotor speed. The same way that we related an electrical angle to a mechanical angle, we can relate an electrical frequency to a mechanical frequency or speed. So this is how fast you're moving the rotor. And that's how fast the flux density is moving through the air gap. So I'm going to put all this together, and I'm going to put the MMF that we were able to derive here together with the permeance, and we come up with a function for the flux density, just considering the fundamental component with respect to theta r, and that is equal to the peak flux density. And by the way, this corresponds to the flux density in a BH curve that you would be looking at. So it's the peak flux density times the cosine of pole pairs times theta r. And that describes this flux density at each position of theta r. All we need now, which we can get from this relationship here, is a peak flux density expression, and that becomes four times mu naught over pi g times the winding distribution factor. I'm writing it as the fundamental part of that. And just to point out that in the textbook, in my notes, I kind of dropped the 1 at this point. So if it says K sub F or K of 1, it's the same thing, times NF, the number of field turns, divided by poles, times the field current. So there is our expression for peak flux density. Another one of the very important formulas that we need to remember. If we want to find the flux that is crossing the air gap under each pole, then all we need to do, we need to integrate the flux density over the area that flux would be crossing to get to this expression here. It's going to be one number. Again, what are we really doing? We're going to be performing an integration over this area here or this area here to find that number. And we're integrating over one pole pitch. So remember that we defined the pole pitch as being equal to 180 degrees over pole pairs, or pi over poles over 2. So I'm going to look at this little example here that I've drawn ahead of time. And this is your rotor. Let's assume we have a 2-pole machine. This is your stator here. And we've got the air gap in the middle. And it's a uniform air gap. And really, if it was a 2-pole machine, I'm kind of splitting it up in half. And this is over each side, saying that this is half of a pole pitch, and this is half of a pole pitch right here. This whole thing is the entire pole pitch. And so I'm integrating from pi to negative pi, or from negative pi to pi, centering everything right here in the middle, assuming that I have a cosinusoidal function. This would be our 0 point right here. I'm integrating from pi over 2 to pi over 2, where 2 represents the number of poles. So these, in general, I could replace this with number of poles. And I'm going to integrate under that area to find the flux. And this is my final result here. Now that flux is a function of the stack length, L sub s, and a function of this number r. Now what is r? I'm defining r as the radial distance from the center of the shaft to the middle of the gap. So that's really saying kind of right in here to the middle between these points. Between the rotor and the stator. What you really have here is you've got physically a radius from the center of the shaft to the inside of the stator. I could call that RS, and I've got a radius from the center of the shaft to the outside of the rotor. So R is equal to the average of RS plus RR. It's right in the middle of the two. The gap is equal to the difference between RS and RR. There isn't a lot of difference here because the gap is usually very small compared to these rotor radius and stator inside radius diameters. But at this point we're going to stop using radius and we're going to use the diameter. So we're going to define D, diameter, here as 2 times R. And now the result that we finally have for flux per pole is this value here. And we can then even go further, because this is in terms of flux density. But if we have information about what the field winding is on the rotor, we could take that information and plug it into here and get this expression here. So these are the, I would say, the two principal expressions that you've got to take away from this lecture discussion that are going to be of importance as we look at a synchronous machine from a purely magnetic perspective. You're going to use this equation 2 or equation 3, depending on the information that you're given. If you only have the peak flux density, you would use 2. If you only have the field winding information, you would use equation number 3. Now finally, I want to put this all together and come up with this flux linkage that I've been referring to. We can consider what is happening on the stator as well. So if you recall, we've been talking so far only about a field winding, but there are a number of windings on the stator that are associated with what we will call the armature or effective armature winding. And next time I'll explain what I mean by that. However, if we do have, just consider one winding, and I'm going to call it a phase A winding. And you probably already figured out that we are going to have 3 windings on the stator, an A, a B, and a C winding. They're going to be 3-phase windings, and we'll talk about that next time. But for any one of those windings, and I'm looking at phase A, we will be able to derive another winding function. This winding function, I'm going to say, is varying as a function of what is happening on the stator. And I'm going to introduce now a very important term, which is called synchronous frequency. And really that's what defines a synchronous machine. We have a synchronous frequency for this winding. The winding has a winding factor which includes both pitch and distribution. It has total number of turns per phase. It has pole pairs. And I'm also going to introduce at this time, because it is an armature winding, a del angle, which you guessed is going to be associated with mechanical torque. And really, I'm reflecting all of these things simply using a winding function. And if I want to come up with a flux linkage that is linking the flux per pole that was associated with the field winding, I simply multiply that flux times this winding function. And now I have a flux linking the field winding to phase A. So I'm showing down here a final flux linkage that I derived. And I have this as a function, as I explained before, as a mechanical frequency that I'm calling the synchronous frequency. For a synchronous machine, the synchronous frequency is equal to the rotor frequency, or in other words, the synchronous speed of the flux linkage i.e. lambda AF is exactly equal to the rotor speed. That is what makes this a synchronous machine. A little bit of a teaser for when we get to induction motors. An asynchronous machine or induction motor, which is a type of asynchronous machine, the rotor speed does not equal to the synchronous speed. So that is the difference between synchronous and asynchronous machines, or synchronous motor and induction motor, for example. Furthermore, since the synchronous speed is equal to the rotor speed, it follows that the electrical angular frequency, omega E, that we're so familiar with, omega E again is 2 times pi times the electrical frequency associated with, say, a supply if this was a motor, or the generated voltage if it was a generator, is related to the synchronous speed by the pole pairs. So multiply the synchronous speed times pole pairs and you get the electrical frequency. Now we have this final expression for the flux linkage of a single winding, and it's with respect to, it has a angle offset, and now this is an electrical angle offset that relates to the mechanical angle offset lambda m by the pole pairs. This is in fact the electrical version of the torque angle that we've been talking about. Prior in chapter 3, module 4, we talked about mechanical torque angle. That would be the del M. This is the same mechanical torque angle that, parenthetically, for the DC machine, the del M was plus or minus 90 degrees, fixed by the mechanical structural design of the motor. So things are clearly coming together at this point. The last thing that we need to do is to derive a voltage applying Faraday's law, and that's what we have here. So if we take the derivative of that flux linkage, we will get a voltage because the rotor is moving, and this is the expression for that voltage. It's a periodic scalar expression. Ultimately, we're going to want to use phasors, and we're going to want to use RMS values. So what is the RMS value of that voltage, this EMF, electromagnetic force voltage? We simply take the peak value here we substituted in here 2 pi Fe, and now we have this expression, and this is the most important expression of this lecture, the EMF expression, which I'm going to put a box around and highlight that. If you know, for example, the flux per pole, you can find this EMF. Recall that this flux per pole is also proportional to the field winding turns and the field winding current, or the field MMF. So this is where I'm going to end it, with us finally having a open circuit RMS voltage associated with a synchronous machine, and this in fact is what you were measuring in lab 5 in the open circuit test, is this voltage.